Differentiation by first principles is one of the earliest techniques that we learn when we're trying to find the gradient between 2 points on a curve. We know we can find the gradient of a straight line. That's going to be this equation up here, m equals rise over run. But on a curve, well, we kind of figure, well, if I draw a line between these 2 points, like so, then what I end up with is a whole lot of parts of the line, the curve here, don't match the straight line between my 2 points. So if I find rise over run of the straight line, that's going to give me an approximation of my gradient, but it's not going to be the exact gradient. So first principles tells us as we slide this point up here, and if we slide that point slowly in along the line, then our h value here is going to get less and less and less and less. Okay, and so what that is going to do is our 2 points are going to get closer and closer and closer and closer together. So eventually we get a point, really quite close into the line. And if I then draw a line between those 2 points, then the curve underneath and the line, they are basically one and the same. So this is really just a version of rise over run. Now, it looks really funky because it's got quite a lot of different notation in here, but let's just think about it. The rise is our change in our y values, so whatever the top y value is minus whatever the bottom y value is, so that's our rise, and our run in this case is the h. Okay, so this equation here then is our first principles equation for finding the gradient of any line. You could use this and none of the rules that we've looked at for differentiation, and this would give you the exact gradient at any point. So this is the rule for differentiation by first principles. So let's use this rule now and apply it to our lesson today, where we're going to find the derivative of y equals e to the x. So up here I've written f of x equals e to the x. So remember, y and f of x, function of x, they mean the same thing. So if we know the derivative f dash of x is as the limit of h approaches 0 of, here's my rise over run, then if I now start to substitute in the information, so f of x plus h, so when the x part in here is x plus h, in my original function, y equals e to the x, it's going to be e to the x plus h, okay, because the x value is x plus h. So the x here is replaced with x plus h. Then I'm going to minus just f when the x value is just x. So that's just going to be e to the x. And then my h value just stays the same. Nothing is going to change there. Then if we go through and we simplify that some more, when I add indices, can you remember what mathematics needs to happen for me to add indices? Hopefully you've remembered that you are multiplying. So if I have the limit as h approaches 0, so the distance between the 2 points is getting less and less and less, then I can now write this using reverse index laws. So this is e to the x times e to the h, because that then would mean I go x plus h, that gives me this, minus the e to the x, all over h. Lovely. So now I can factorise that. So the limit as h approaches 0, as the distance between my 2 points gets closer and closer to 0, I'm going to factorise out. See how I've got an e to the x here and an e to the x there? I'm going to factorise that out. E to the x, and it'll be e to the h minus 1 all over h. Now, as this h value here changes, it's only going to impact what's inside the brackets here and the denominator. So we can kind of treat this e to the x as a constant. So what I'm going to do is I'm going to write that and pop it out the front. So e to the x, and then it's the limit as h approaches 0 of that e to the h minus 1 all over h. So this formula here calculates for me the gradient. So let's just remind ourselves of that. So it calculates the gradient. All right. Now, well, as h gets smaller and smaller, what does this term do? So let's investigate that. So we'll go over here. So I've done up a little table, and this is also in your book on page 137. So as h gets smaller and smaller and smaller, you'll notice here that that term that we just looked at, the e to the h minus 1 over h, that number just gets closer and closer to 1. So basically what's happening is my f dash of x, which we know is e to the x, and then it's really times the limit as h approaches 0 of e to the h minus 1 over h, we are saying that that fraction term, this term right here, this is approaching the value 1. Okay, as h approaches 0, this value here just gets closer and closer and closer to 1. So really then, what I've got is my derivative then, my f dash of x, is really just going to be e to the x times 1, or just e to the x. Now, this is kind of cool because if you remember, our initial equation was y equals e to the x. And what we are saying is that when we find y dash, that is also e to the x. And this is one of the only equations where you differentiate it, you end up with the same function you started with. So that's why exponential functions are quite unique. So remember here of notation though, I can write this as y, I could write it as f of x equals e to the x, which would mean this would be written as f dash of x equals e to the x. So what I've done here is I've just stepped you through using first principles notation and shown you that the derivative and the original function actually are one and the same. Hopefully that makes sense.